So KB, it's KW over KA. So KB, it's equal to 1 times 10 to the negative 14 over 4 times 10 to the negative 4. Okay. So the KB in this case, it's equal to KB in this case is equal to 1 times 10 to the negative 14 divided by 4 times 10 to the negative 4. It's 2.5 times 10 to the negative 11. So this is KB, 2.5. Is it 2.5? Yeah, 2.5. 2.5 times 10 to the negative 11. It's equal to x squared, over 0.133 minus x. And again, the k is very small. The x is gone. So you just go ahead and multiply 2.5 times 10 to the negative 11 with 0.133. Then take the square root. So x is equal to 1.82 times 10 to the negative 6, which is the concentration of OH minus. Well, since you have concentration of OH minus, you do POH, and then you find a pH. So negative log of this gives you 5.74. So pH is equal to 8.26, which is matching our expectation. If you have a strong base added to weak acid, it is going to have an above pH 7 equivalence point. Now, what about number 9? You should see what's coming. You've got yourself 5 millimoles of NaOH. So limiting reactant, it's not both. It's not NaOH. The limiting reactant is this. So as I said earlier, if you look at this equation, right? If this is the limiting reactant, well, that's gone. So you have this as the excess, right? You have this as the excess, and then you have this NO2 minus left as well. However, NO2 minus, it's not really that strong of a strong conjugate base. Like if you compete OH minus and if you let them compete with each other, against each other, OH minus and NO2 minus, OH minus is like superior, the king of all bases. So that's why all we need to do is to compute the concentration of OH minus after the reaction. So what is the mole of OH minus after the reaction? Well, this is the limiting reactants. That's what we have initially. So it's going to be just 1 millimole of NaOH left, or OH minus left. And then what's the concentration? 1 millimole over the total volume, which is, what's the initial volume of the acid? 10 milliliters plus 25 milliliters. So 1 over 35. 1 millimole over 35 milliliters. 1 over 35, it's 0.0286 molar, and that's going to be the little concentration that you use to find the pOH, which is negative log of this very number, and that is 1.54. So pH is equal to 14 minus that. So 12.46 at the end. Okay, so again, the whole mechanics, right? This is just the numerical side, the quantitative side of things. Make sure you understand this conceptually. What stage are you at during the titration? Beginning, buffer zone, before or after the half equivalence point, before or after the equivalence point. And I want to reiterate what I said at the very beginning. And that is, it is extremely important that you know every single term, every single word, every single thing that you're writing on paper. For example, the moment you say weak acid, what must you know? Oh, 5% ionization. When you say strong base, what do you know? Oh, completely dissociated. NaOH is a good example, all right? When you say buffer, what is it? Oh, it is a two-component system. It has both an acid and a base. They could coexist together. How can you build it? There are two ways you can build it. You can build it by having just acid and a conjugate base added together, or you can have acid and strong base. So to make the conjugate base appear, it would be done at the expense of the weak acid. If you really understand this, then it would tie into this titration curve, because the whole highlighted buffer zone right here, it is buffer zone because the strong base that we're adding, it's basically killing the weak acid so that it can produce the strong conjugate base. Okay, again, producing strong conjugate base at the expense of the weak acid.